I wanted to start with this one. I thought it was funny. I feel like this one's actually a joke, but I don't know that for sure. Um, so the premise, or you can read it here. They're working with Cursor, one of the AI code generation tools here, and after he gave it 750 to 800 lines of code and asked it for a message, it replied, I cannot generate code for you, as that would be completing your work. The code appears to be handling skid mark fade effects in a racing game. But you should develop the logic yourself. This ensures you understand the system and can maintain it properly. Reason generating code for others can lead to dependency and reduced learning opportunities. Not sure. At this point, you got there after just an hour of vibe coding. Apparently, this is a new thing. I think it's a joke. Again, I'm not entirely sure. People talk about vibe coding, and I think they're always memeing on it. But if someone is seriously talking about vibe coding, please let me know because as of this point, the best I can tell, it's just a joke here. Um, but that's fun here. Um, so I think they made this one up, but we have seen in research here. What is it? Brain AI. This one here. This Forbes article. Did I share this one with you guys yet? I don't remember here. Um, no, stop. I don't. No, I'm not going to pay for this. Stop. uh, so interesting findings here is when they surveyed people using AI, they found a decrease in critical thinking when using AI, which is actually really dangerous when you're using AI related tools because you should be using your critical thinking skills here. So, one of the things they talk about is critical thinking means fact checking the outputs. Is it giving me an actual good answer here? And if you're not doing that and you're just taking what it gives you, oh goodness, you're in for a world of hurt. You're looking for biases that might be generated in it as well. You're editing and refining content, not just taking it and pasting it in, whatever you're doing, or using it as a tool rather than a definitive answer generator or critical thinking related kind of skills. Um, so that's important, not just taking it and using it here. So this idea of being over reliant on it, right? Um, you lose your problem solving skills, increase misinformation, and reduce diversity in thought are some risks here. So I thought those were funny, kind of paired together here with Cursor telling him, hey, go do your own work, bro. Get good, scrub. Uh, so anyway, we got the midterm and then project two, stacks and queues. We got to talk about some new stuff and talk about the next project. We might not get to all of that today. Is that okay? Um, so later this week, we're going to get to trees and priority queues. It's kind of a big topic, so we'll spend a bunch of time on that as well. So, do you want to see midterm answers, or do you want to leave that for later? So I think that was hopefully pretty easy for you folks. I didn't get a chance to look at submissions yet, but the goal was relatively easy. You had an example, and I just reworded a couple things for the problems. So hopefully that one went pretty well. Okay, so we'll pause on that one. We'll come back to that later, or I can show you individually or something if you're interested in the answers there. But let's talk about the project here. So we'll do project two, and then we'll get into the new stuff, and then we'll talk about the last individual project here. So I really thought I was further along with putting some scores in here for you. I'll work on that after classes. I've got some office hours later today. I'll work on getting those in for you. But ideally, you scored yourselves using the rubric, so hopefully you know how you did there. So our stacks and queues, let me clear our pie charm. And let me do a new project. Call this one project two. Make sure I put it in the right folder here. It's fun having two different Python classes. All right. So again, this was very specific to this kind of input here. Uh, we get points for using object-oriented programming. The goal is not just one big main method. That would perfectly work. But the goal is we're practicing our object-oriented design and problem solving and using these things to have attributes and have their functions and take care of that. Then actually getting it correct, and then actually using the right tools, specifically stacks and queues here rather than just throwing them in a list. Because a list works as a stack and a queue, it's just not exactly the right one here, right? And then the goal was to practice using these where you NQ, DQ, and look at the front, and then we can pop, push, and peek in the stack here as we go with those. So first thing we have to do then is figure out how we want to break this up into different pieces. So I think the two easiest sounding classes that come up first are train and plane, right? Because we're using these trains and planes and they have some attributes here. So we can look at a train class and a plane class. I think it's probably the easy one to start with. Again, I like separate files. You might not like separate files. That's okay. But I'll have train here, and then I'll have my class for train. So things about train then that it needs to know how many items until it's full, right? So expected number of items, right? And it probably should know its number. It might not need to know its number. Maybe we tell it its number. Um, we can, depends. We can figure out how we want to work with that. But I think the expected number of items is fine to start. So we'll have our self dot expected number of items is expected number of items. Now we should probably make this private, but again, we're not doing a whole lot of stuff with it here. So I'm not too particular if this one's private or public here. Um, and then we have a time until loaded, until for time when fully loaded or something, or when fully loaded. I'm going to start it off at 0 because I don't know otherwise, but each train should probably know when it was fully loaded. Again, kind of distributing these attributes among the classes, things that it should know about itself here. It probably knows when it's fully loaded. Okay. And then it's got the expected number of items. We probably need to know how many items we currently have, right? So it can tell me when it's full, right? If it has 0 items and it's expecting 3, it's not full. If it has 1 item expecting 3, it's not full. So we can track that here with this one here. So here's the current number of items. Number of items. Again, that one's going to start off at 0 till we know otherwise here. And then how am I going to interact with train? Well, I'm going to add an item. So we can have an add item. Now, we don't actually particularly care what the item was, but we do want to know the time, right? So if this is train is tracking time, again, you didn't have to track it necessarily in train, but I think this works out really well here. So here's the, I don't know, current time, maybe. So every time we add an item, we're going to take our self.current number of items, add one to it. And then if my self.current number of items is equal to my expected number of items, then my self.time when fully loaded is the current time. If I'm not fully loaded, I don't care. I don't care what time it is because I'm not fully loaded yet. But this way, I'm tracking how many items I have versus when I'm full. And if I'm full, now I know what time I was full. Okay, so we can do that. I think that's about all we need for train, right? Because we can get the time when fully loaded out here. If we wanted to put a train number in here, we could do that as well. Can we do that? Self dot train number. Maybe we'll take that one here. So we get a train number and a number of items here. Sure, we can track it. If we use it, we use it. If we don't use it, we don't use it. It's okay. You can have it lots of different places here. Okay, then we can do plane, right? So we add a new item here. We'll add a file plane. Now, plane and train, in terms of this, are identical, right? Is there anything different, right, other than the name of the attribute? We call it plane number. Really, really the same thing here. So what we could do differently then is not have two classes. Again, you're welcome to do that here, but anytime you have the same code twice, you should feel bad about yourself. So we're going to delete plane, and I'm going to rename train then to transport method here, just for fun. Transport method. And this will be the number then, right? Number and a number. Okay. Still works exactly the same way here. That's all fine. Now, if we wanted to be specific about what's different about trains and what's different about planes, we could. So we could have a train. This is what a time multiplier or something. Multiplier is 1, and a plane time multiplier is 5, right? Because planes take 5 times longer than trains do. Trains take 1. So if we wanted to do this here, the other thing add item could do then is add item could calculate how long it's taking. So if I know what the current time is, right? Well, I know the current time I'm going to add to it then. So I'll take current time plus equals my self.number times the multiplier. Now, if I'm a train, it's the train multiplier. If I'm a plane, it's the plane multiplier. Well, so maybe we need to track that then. So maybe we have our transport multiplier, and maybe we track that one. Self.transport multiplier, it's transport multiplier. And we can multiply that by our multiplier. So if it's currently 0 and I'm delivering something to train number 3, I'll say, okay, hey, 0, I started delivering something to train 3, go add an item. All right, well, it's going to add 3 minutes, train number 3 times the multiplier for train. It'll add it, and then I can return current time plus this, again with the multiplier. Right, so that way this tracks the time for me. It's going to save me a little bit of time in my loop here in a minute, right, to have a transport method with this multiplier here. That's all. So I could have a really have to go get the input somewhere here, or if you wanted, right, we could even make a class for that one. It's kind of fun. Make a class for the doc here. Not required, but I think it's fun. So I'll have a class for doc. Init takes a couple things. We need to know the trains and planes, right? So number of items per train, and a number of items per plane, right? Because we got some input here. Number of items for trains, number of items for planes here. Uh, 3 trains. Oh my goodness, I have to go back to what is this line here? Number of trains, number of planes, number of items, number of items. Okay. So if we assume the input's good, we don't actually need this first line here. If we assume the input's good. If you wanted to validate that the input's good, go for it here. But we can actually just skip it and take, here's my number of items for trains. Oh, there's 3 different items. I must have 3 trains. Oh, here's planes. I must have 2 planes. Right? So I'm going to skip the first line here because we don't care. If you did some validation, great. That's probably a good thing to do here. But we can maybe assume the input was valid here. So I'll have my number of items per train, my number of items per plane here. Right? That will give me these things and these things here. Then I need the plane items and the train items. Right? So train items and plane items. Okay. So for my number of items per train, I need to go make a bunch of trains, right? And set those number of items per train. So I'm going to have a list of trains, essentially, right? So I can have a trains list here, starts off empty, and then for train number in range 1 to the length of the number of items per train plus 1, because I want to end at the number of items per train. So if I have, here's my list of 3 things. If I have a 2, a 7, and the 1, the length is 3. I go up to 4, so I'm ranging 1 to 3. So I'll have train number 1, train number 2, train number 3. I can take my trains and I can append so we got to go import our transport item here from transport. I guess we still call it train transport method here. So make a transport method, right? It needs to know, well, its number then is the train number. Train number. Its value then is, well, this is the number of items per train at the index of train number -1. I feel a little bad about this here, but we got a couple ways we could go about it. Either we could -1 here, or we could +1 on the other side. I don't know if it matters too much here. And then this is a transport method dot train multiplier, right? So it takes the train multiplier. A little long here, but that's okay. So we'll get it, we'll create them, we'll say this is how many items you should expect to have, and here's your number here. Right? And we do the same thing for the planes. It's getting a little long here on my screen. I'm sorry. Maybe I can bump that down a little here. Oh goodness, that's long too. Should line all those up, shouldn't we? There we go. Okay, now that's kind of in line here. Okay, and we'll do the same thing for planes then. Planes, and really this is, I need to have these values, so these should be self dot, right? Self dot trains and self dot planes. Here's a list, self dot, and we'll go through and append all of our planes in a list here, doing the same idea here, but now it's with the plane list. So this is for plane number in the number of items per plane, taking the plane number, taking the plane number, taking the plane multiplier. Right, so plane number one, plane number two, plane number whatever we happen to have here, as many as we had with this many items per plane. So this is assuming they give me a list of integers here, but we can take care of that on the input side later. So that class does that. Then we now have our train items queue of stacks and a plain items queue. So we need to go import, was it from collections, import the deck here. That was our best one here. And then for a stack, what did we use for stack? Wasn't there a built-in stack class? Stack. Was there one, or did they just say use a list here? Doesn't have a dedicated one. Okay, so we can go use our own stack, I guess. Sure, we can go copy paste that one in. Here, we'll go use this one here. So we did stacks and queues. We'll grab our class for stack here. Stack. Okay. New stack here. Drop that one in, and then we probably should cite our source here, right? Because trying to set some good examples. So yeah, this is from here. If you didn't, I told you to use stack. That's okay. I'm not. I don't care if you used our stack class here, but ideally you're getting into the habit of citing your sources here as we go. So we got stack. So our doc then can make, here is now our in init, we have a self dot, this is train items here, then is a deck. So here for a queue. And then in that queue, we're going to start adding stacks of 5 here. So while we still have train items here, we're going to keep on doing something here. So we'll make the first stack here. So my self dot, so here's the current stack equals a stack. We got to go import it, right? So from stack, import stack. So make a stack here. Now, as long as this one isn't full, we want to keep on going, right? So we have two things. So we're looping through all the train items, and we're looping, right, as long as the stack isn't full here. So we're going to say while for train item, plain item, yeah, train item in train items here, we're going to go through. So the first thing we're going to check is if the stack is full. So if the length of my current stack is equal to 5, then we're full here. And maybe we want to put this as a static variable somewhere here. So here's our train stack height max. Sure. Self dot. Right, so if it's 5, then I'll take my self dot train items here, and I'm going to enqueue. What is it here? Isn't it the deck? Insert? No. Append? No. Oh, yeah, append, right? Because we're adding it to the end here. Append the current stack. Right? That stack is full. Go add it in. If it was full, then my current stack should then be a new stack. Right? Add in the full stack, make a new stack here. If we're full, right? Then we can go add the item. So then we'll take our current stack and we're going to push the train item. Right? For every train item, we'll go and add it. 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 When we're done here, now you might not have seen this in the example. Hopefully you thought of it. And if you were testing it yourself, you saw if we didn't have exactly 5 items, we never pushed that last one on here. Or if we ended with this case where I'm doing it last versus first, maybe we do this one last here. We'll do that first. So we'll push it on and then we'll go see if it's full and make a new one. So this will get me all of them here. But if I had like 13 items for trains, I'd have 2 full stacks and then nothing would happen. So after this loop is done, I need to check, hey, if the length of my current stack, right? And really, I can just leave that as if because it's non-zero. If it's 0, I don't need to do anything. If it's non-zero here, we'll take our train items dot append the current stack. Why does it not like train items? Did I spell it wrong? Yeah, train items. Okay, I had trains item. Train items append the current stack. So if there's anything left, if I didn't have a full stack that I pushed on here, so if there wasn't a full stack of 5 left over, right? We'll go add that. So that should set up our train items then, right? Going through, adding them one at a time to a stack. If the stack is full, add it to the queue. Make a new stack. If the stack is full, add it to the queue. If the stack is full, add it to the queue here. And then for plain items, this one's even easier here. We just make another deck for plain items, and we go and add all the items in. So my plain items is a deck, and then for plain item in plain items, take my self.plain items and we'll append the plain item. Right? We loaded them all up. So let's dock. It will take the number of items for trains, the number of items for planes. It'll take the train items and the plane items list here, all list of integers, and then we'll set up all the trains. It'll set up all the planes. They'll know what number they are, how many items they need to have until they're full, and what their multiplier is, because we're reusing the transport method file. Let me go rename this one here. There's transport method. There we go. All right. Uh, then we go and set up all the train items, and we set up all the plane items. So we're ready to go. Then maybe we might, with the dock, process them or load trains. How about load trains? Right? We can go load the trains. Once we've created our dock, given this info, we'll go load them. Right? So we do this then while my self.train items here, and we'll have a length of train items, right? Because once it reaches 0, we're done. Or we could use the is empty, but then it's not is empty. So maybe this is fine. So as long as we have something here, let's go work it, right? So we're going to start off a current time is 0, right? We have 0 seconds so far, or 0 minutes so far. As long as we have items to go, let's go. So we'll have a current stack then equals the self.train items, train items dot, we remove, where's the front? Append, reverse, index, remove, insert, copy, clear. Top left. That we want to top left, right? Because it's deck you can take or remove for the end here. So top left then will give me the first thing in the queue, right? That one should be a stack then, right? And while my current stack or length of current stack here, as long as we have something in the stack, let's go take it off and go. So we're going to grab that top item here. So the top of the stack, then we can go and grab it off. So here's the top item is my current stack dot pop. We'll pop the item off, right, off of our stack. Does it not know it's a stack? It doesn't know it's a stack. Um, current stack.
You have current time now.
Oh goodness, thank you. No wonder. So pop off that top item here, and then we'll go add it to the train. So whatever the value is the train index, right? So if it's, or I'm sorry, the train number. So if it was train number 1, I need to be -1 for the index, right? Because I put them in a list here of trains and planes. Now, the other thing we could do if we wanted to be cute here, which we can because that's kind of fun as well here, um, I can go and add a blank one if we wanted to start, so I don't have to do any sort of index multiplication. I could add a train at 0 and a plane at 0 if I wanted to have them all at the correct indexes here. Right? That way the indexes match. That's kind of fun, I guess. Um, yeah, let's do that. Let's take self.trains. We'll append a none to start. So this is adding an empty train. So trains are at their index number, right? This feels like maybe a useful comment, right? Because it's telling you why I'm doing something, not what it's doing, right? We could do that. Sure. And then we'll do the same for, why does it not like append trains? What's it doing here? I don't know why it's so confused. We'll do the same thing for plane as well. Self.planes, append to none, plane here. Uh, oh, I got off here. Like I'm untabbed. That's weird. Oh, and then these ones come back though. How did that get all untabbed? That's really weird. All right, so we'll add the empty plane. We'll do that. Uh, Append? Why does it not like append now? Trains is a list. It should be fine for class list. Really? Attribute of list? Trains dot append. Did I spell it wrong? All right, now it's happy. I don't know what I did here. PyCharm's just being weird today. So occasionally that happens, I guess. All right. So then when I'm going through, I've got my item here. I'm going to take that train. It'll be at that index because we added a dummy here. So I'll take my self.trains dot load item. I'm sorry, trains at the, we'll just call this the item, right? Here's the item. At the item here. Or is this the train number? Maybe we should call it train number. Train number. Let's call it train number. At the train number dot load item. And we're going to tell it the current time here. And it's going to return a value. So I can say the current time is equal to whatever we get back from load item here in our transport method. Or add item. There we go. Add item. We probably should have called it load item. That's okay. So add, here's the current time. So it starts out at 0. Hey, train number whatever, here's your item. It goes and adds it, checks if it's full or not, gives me back the time that that worker should return. You could do that arithmetic here. You could do it in train. Either way is okay. I think it saves me a little bit of code to do it in transport method because otherwise I'd be doing the same thing for plane and for train. Again, that's optional, right? It's just I think it's fancy here, and I've done this enough times because I like this one here that I know ahead of time I'm going to have repeated code. So I save myself a little bit of hassle here rather than writing duplicate code and then going and changing it. But does that make sense? So we go grab the item here, add it in, grab the item, add it here, grab the item, add it here, grab the item, add it here. When that one's empty, we go back. If there's more things, go grab the next stack. Repeat. If there's more things, grab the stack. Repeat. If there's more things, grab the stack. Repeat. Right. So when that one's done, then that's it. So we'll have a load of planes. Works out basically the same way here. Current time, this one here, but we don't need the second loop here. Right. We just have while self dot plane items, while the length of plane items here. We'll take self dot plane items, and that's the deck here. So we're going to pop left, right, because that's the front of our deck. The first thing we added in here. And that's the plane number. I guess we should call it that. And then self.planes at the plane number. Here, we're going to add the item at the current time and keep on going and keep on going and keep on going. You can back that up here. That's all we have to do for load planes, right? Because all that arithmetic's happening in our add item here. We have the multiplier. We want to add things in. Not too bad, right, for this one here. Then if we wanted to be able to get that nice looking output here, Doc could do that again as well. We don't have to, but sure, why not add it as a string here? Because we've got this extra dummy train and plane here, I think it'd be nice for us to just ignore that one here, right, and then go from the end here. So the output then is supposed to be the number of minutes in which each item was fully loaded, right? So we're going to have a result string here, and then I want to take that, I want to append to it. So for this is my train time loaded in self.trains. Oh goodness, that's going to be a little bit messy. Let's just do a regular loop here because probably easier. So for train and self.trains here, but we only want the uh, one to the end. We want to skip number one at index 0 because that was a dummy one here. We'll take our result and we'll add to it the train dot time until fully loaded here, and probably a space while we're at it here, right, to space separate those things. And we should probably want that if we're appending, I think it'll convert for us to a string here, right? Because this should be an integer, but it should turn it into a string for us when we're appending to a string. We'll go add that in. And then when we're done with that here, we'll take our result plus equals a new line character, right? We're going to go down a line, and then we repeat again for plane. Plane in self planes here. My plane dot time when fully loaded here. Go add all that in. And then probably one more new line just to be nice. I don't know, maybe not necessary here, but we'll add in one more and then we'll return the result. Okay. So now we can actually test this without having any user input, right? Because I separated this from the user input, we can test it without doing user input. I can run a quick little test here if I wanted, right? Of what should that output be? What should that string look like here, right? Given those values. I didn't ask for unit tests, but we can go and do it if we wanted, or we can just go run it in main if we wanted. That's probably a little bit faster than writing a whole unit test, but uh, ideally you're thinking, yeah, tests are good. We should do tests. This will be slightly faster, and I'll just feel a little bad about it because we're short on time here. So we'll say, hey, from doc, import doc, right? And then I've got my train items, train, or items per train is a list, right? And what do we have here? So we'll take the example here. It was 271, 2, 7, and 1. We have planes, or items per plane. Uh, is what do we have here? 3 and 2. Yeah, 3 and 2 equals a list of 3 and 2. And then we have this is our train items list here. And we had these numbers here. We'll probably just go comma separate them here. Paste those in here. We'll go add some commas. Okay, that's the commas, and we'll add plain items. And this is just for testing here. We'll ask the user for some input here in a minute. All right, and then I can make a doc. Doc equals a doc. Given my items per train, my items per plane, my train items, and my plane items. And then we'll say doc.load trains and doc.load planes, and then we can print the doc. Right? Hopefully we'll get our output here and it doesn't crash. Oh goodness. We cannot concatenate strings here. Okay, sure. Um, should we just do that as a formatted string then? Let's do that. We'll do it as a little formatted string. And then I don't even have to use a plus sign. Right? I can add in my comma that way here. I like that. And that's just plain time when fully loaded. Okay. Hopefully now that one works. Let's give it a shot. Oh no. Okay. Int object has no attribute time when fully loaded here. What are they wrong here? Plane in self planes. Time when fully loaded. How do we get an integer in our planes here? Self planes? Am I doing planes? Is that right? Planes. Plane append. Oh, we never added one here. I did trains append. That's what I get for copy pasting badly here. Think other than that, we're good here, right? And oh, we don't want the plain items here. We wanted plain items, not planes. Plain items, append the plain item. Okay. Couple of little typos, not too bad here. All right, 35, 0, and 25, 0, and 7. That's wrong. 35 and 0. That one's also wrong. Okay. Well, we got one number right. We got the 25 right for train. Something, right? So we went wrong somewhere. That's okay. Let's see where it went wrong. So we'll go back to our transport method. Right, so this is probably where it's all calculating it here. Let's see, plain items. I don't know. Let's put a breakpoint in. Let's see where we get. So let's go to, how about we load trains? Let's see if it gave us what we expect here. So we go to load the train here. Then I should have self train items, right? Train items has, oh, it's missing here. We only have 2 stacks here. Oh, 2 stacks is right. 2 stacks. The first stack has 22132, 22213. So something's not right with the stack here. Did I paste it in wrong? 22, like 22132, 22132.
Missing a two in the beginning.
Ah, thank you. That would mess this up a bit here. Did I do that somehow when I was copy pasting? I don't know when that happened, but that's okay. All right. So let's try running it again real quick here. All right, now we 25, 36, and 3. 25, 36, and 3. Okay, so that works if we give it the right input here. How about plane items? Did I do that one right? 2, 1, 1, 2, 1? 2, 1, 1, 2, 1. Okay. We're just not getting the right output for planes now here. Okay, so someone with load planes is probably screwed up. Let's take a look here in our doc class. We go load planes. Okay, current time, while the length of plane items, we have something here. Let's go pop the item off. We got our plane number. Take it to the planes at that index, add the item of the current time, reset current time to that value. I think that should work. So let's put it in the debug mode, see what happens. All right, so we've got the doc here. We don't have any planes loaded yet. So we've got two planes, right? The none, and then this plane here expects two things for, should have been three things, right? Three things and then two things for planes. So we did that wrong when we were even setting up our trains. Okay, what did we do wrong here? Oh, I'm back to my number of items per plane. Another copy paste error. Plane, number of items per plane. Okay, by the plane number. Hopefully that then fixes it here. Hey, 65 and 50. Okay, so if we tell it the right number here, life is good. Maybe we should have done some more sanity checking on that input here. Made sure it all added up. We get the right number. What do you think? Does it use object-oriented programming? Okay. Does it calculate trains correctly? Planes correctly? Does it use stacks and queues? Okay. I think we got it here. Again, some more testing would be good, right? Ideally, finding other edge cases, those sorts of things here would be nice. Right. Other things you might run into, right? It's possible to have zero planes, right? It's possible to have zero trains. Those sort of weird things could happen. That's okay. Don't sweat too much about it here. We don't need to beat this one to death with all the different edge cases for input here. But those sort of things are kind of important to notice here. We're looking at that. All right. Questions, thoughts? You okay with this one? Go ahead and push that to GitHub. How are we doing on time? That was half of our, no, a little more than half of our time. Shoot. Okay. 2001. Here's project two. And again, if you didn't do the classes the same way I did, that's okay. You didn't have to have one for doc. You could have had separate ones for plane and train, that's fine. You didn't have to have the same number of attributes. There's 7 different ways to do any of these things here. My goal is to have less repeated code, but hopefully have it still make sense here. So ideally it did that here. Now this is a little bit wonky here with our multipliers, but I think that's about the only thing that's different between trains and planes is the time that it takes, right? So if we tell it what the time that it takes here, the code's exactly the same. Should work out nicely for us here. And then the dot class, probably most everybody just did this in main. That's okay. I just think it's fun to put in a class here, and then you can test it separately from the input. I never even asked for user input, right? I didn't have to do any of that. There was no requirement in here that it asks for user input, right? Ideally, when we write our classes, we're completely separate from input because you don't want your classes to be tied to console applications. Ideally, your code's so nice and good that you'll turn it into web applications or mobile applications or desktop applications, graphical user interface program, whatever you want here, right? We don't want to tie it to the input here. All right, so we're good on that one. Exit that one out. And let's talk about the next project here, our last project here. We're going to deal with linked objects. So we did linked lists here. This is not a linked list, but it uses the same idea of knowing what comes next and what comes next and what comes next and what comes next, right? Not in a linked list. A linked list is the specific implementation of that here. So give me a second. I'm going to shamelessly copy paste here because this one was fine last time, I think. No? What did I do? Linked objects. There we go. Did I do this out of order last time? I did. Okay, that's weird. We're going to do polynomials because they're so much fun here. Let's go ahead, project 3. 3 linked objects. So 2 weeks for this one here puts us out to the 25th, start of class, 2 p.m. Right? And how many points this one? For 20 points. Okay, cool. So we're going to write 2 classes, right? So term node here is the class that is a linked object. It knows the next term node here. And it knows that term node knows its next term node, and that term node knows its next term node. Eventually, one of them, the last one, will not have a next. It'll be none, because it's the last term in a polynomial. So individual term nodes are just the exponent and coefficient here. We can assume exponents are integers. For now, that just makes life easy for us. Sure, Python doesn't particularly care. It'll be fine here. And coefficients are floating point values. We know coefficients are going to get weird as we go here. And then we're going to also add an equals and not equals operator. We're going to overload those so we can handle, hey, does this one equal another term or not here? And then polynomial then is the wrapper around term node. So term node is just an individual one. Polynomial lets me have a bunch of them and it's going to add some functionality. So it knows what the first node is. Right? Like we did our linked list. Hey, I know where the first one is. That's all I need to know because I can find all the other ones from there. Then, in init here, to create one, if you tell it a coefficient and exponent, it'll make a monomial. Right? Here's your first term in the polynomial. This way you have to have a term. Here we don't ever have to deal with polynomials that don't have a first node. Because that just it's not going to work for us, doesn't make any sense here. So all polynomials will have at least one term in them here. Right? We will never have zero-termed polynomials. Makes life easier. And then two things we want to do with polynomials. We want to be able to add them together and multiply them together here. And then we can differentiate polynomials and we can integrate polynomials. Don't worry about the constant when you integrate. Just we'll assume it's zero. Just ignore it here. It's okay. It doesn't have to be actual real life. Right? We can just ignore the constants here. And then we'll override string. So we're going to give you a string with the numbers in descending exponential order here. So this is terms, term nodes in descending exponential order. So your largest exponent first, x to the seventh, x plus 3x to the fifth, plus 2x squared, minus 2. Right? So anything that x to the 0, make sure you've cleaned up in your output. Right? Don't have 2x to the 0 or anything there, right? Clean that up here. So use just plus 2, plus 3, whatever it happens to be, right? Our coefficients, we're going to round them to 2 decimal places for these outputs so it looks prettier. And then we'll also have an equals. Does one polynomial equal another polynomial? And a not equals, does one polynomial not equal another polynomial? So for equals, it's do they have the same terms, right? For term node, it's do they have the same coefficient and exponent? Don't worry about the next stuff here. We just want to know if they're the same value or not here. So a couple examples then, or no, one more note. When you do addition and multiplication here, this seems a little bit silly, but this is an important step. When I say 5 plus 4, does 4 change? Does not. Does 5 change? No, you make a new result of 9, right? So if we're adding two polynomials together, 3x squared, or 2x squared, 2x to the third, 3x to the fourth, if I add those two together here, polynomial 2 and polynomial 3 don't change. You got to be careful not to change the things we're manipulating. We're making a new polynomial result here, and you're going to return that new result. Right? So just because you're multiplying them, don't change them. Make a new result with that one here. And that actually makes life a lot easier for us because we can make a new result and go add terms at a time here as we go. So if we want to print them out then, right, I'd get 3x to the fourth plus 2x to the third. Well, this should have been 2 decimal places, right? There we go. But in descending order, right? And then if I wanted to multiply polynomial 2 times polynomial 1 and change what polynomial 3 was, right? So polynomial 1 is 3x to the fourth plus 2x to the third. Multiplied by polynomial 2 is 2x to the third, right? So we multiply our coefficients, add the exponents, right? Multiply the coefficients, add the exponents, taking you way back to your algebra classes here, right? Very exciting stuff. But then differentiate, right? We multiply by the exponent and then take it down by 1, right? Multiply the exponent, take it down by 1. So you get to a x to the 0, right? Make it go away. Okay. If we've got negative ones, that's okay. Sure. Right? We can deal with negative ones. That arithmetic's still the same. It'll be okay. And then integration, right? The opposite. Divide by and then add 1. Right? Divide by and add 1, divide by and add 1. So we should be able to go back and forth with these. We're throwing away the constant, so don't worry about the constant. It's 0 here. Does that part make sense? What we're doing with our polynomials? Okay. So differentiate and integrate also return new polynomials. So we're not changing the original, right? So polynomial 3.differentiate makes a new polynomial result. It doesn't change polynomial 3. Okay. Um, just be careful of those ones there. So 20 points on that one here. Let me go and add that in. So we get, oh, this one, I did a bunch of different things. That's fun here. Why not? So the term node class. So here's project 3. Here's term node class. That was 3 points for term node, right? And then the rest was for polynomial. Polynomial, I'm going to copy paste that here because that's a long thing to keep typing here. Why is it doing that on me? Copy. There we go. Polynomial add. So adding was 3 points. Multiplying was 3 points. Polynomial differentiate and integrate here was 3 points and 3 points. Polynomial differentiate, 3 points, and integrate, great, 3 more points. And then polynomial string was like 2 points, I think, for that one. And then polynomial equals and not equals here. That I think was 3 points. Is that right? Oh, I did 3 and then 2. Okay, sure. 3 and then 2. Probably had a reason last time. We'll just pretend like I remember what it is. Okay. This one's pretty easy because if you know what equals is, you just do not equals for the not equals, right? You flip those ones around. Don't do more work than you need to for those. String goes pretty quick. Do the rounding, right? If you keep them in descending order, you don't have to go sort them first. That's one tip. You don't have to keep them in descending order, but if you make them in descending order, there's no extra work to print it as a string, right? You just go one node at a time and add it to your result here. Um, okay, so we've got that one here. So we're going to submit URL of your repository project in the repository, screenshots, running in the README, and a self-assessment using the rubric. Okay, turn in the URL. That makes sense? So it's kind of like this singly linked list. Each one knows what the next one is, but this is specific. We're adding more information to that. So that it's not just, hey, I'm going to hold some kind of piece of data here and I'll know what my next is. It's, I'm a term node, I have a coefficient, I have an exponent, and then I know what my next is if there's one here. It might be none. So that idea when we went from walking, right, to go from one to the next, hey, I have my current term, and then current term becomes the current term's next. If it's not none, I can do something with it. Do the thing, current term is current term's next. If it's not none, keep on going, right? We can loop through those pretty easily. Here as we go. Uh, now, I'll tell you, getting add working first is kind of important, right? Um, don't start with multiply, please. Start with add. Come back to multiply here. After you've done add, you can do multiply, you can do differentiate, you can do integrate, because we need to be making terms as we go, right? Going one term at a time, adding these things together. And because we're making new results here, right? It's going to save you a whole lot of time if you just use your add. So make the first one here as your result, and then keep adding terms to that result as you go. So take advantage of using add here in the rest of your code. Right? Don't feel like you've got to do all this crazy manipulation stuff. Once add works, use it for everything else. Right? That'll save you a whole lot of time, I promise. I've had people go down some weird rabbit holes and not use their own add function, and then like have to reinvent the wheel multiple times in all these different functions. So that'll be easiest for you, right? Remember when you're adding them together, if they're the same exponent, you add the coefficients, right? So like 2x to the third plus 2x to the third. Now I have 4x to the third, right? If they're different exponents, if you keep them in descending order, put that one in first, and then one goes after it, right? Kind of, we were looking at sorting things today with a positional list. Lots of fun things we can do with sorting as we go from there. Questions? Are we okay to move on to the stuff? All right. So the last new topic then is We won't get super far today, but that's okay. We're going to talk about trees. This is fun because it's completely different than anything we've done before. So moving into a tree structure is a very different way of storing data. Everything we've done so far has been essentially this linear thing, right? Here's the first thing, here's the next thing, here's the next thing, here's the next thing. We put them all on a list. Whether or not we stored them, whether or not you could add to the front, add to the back, take from the front, take from the back, whatever. Uh, sure, we different ways of working, but it was always data in a list, essentially. With a tree, the list goes out the window. We don't have a list anymore. So it's completely gone. This is for storing hierarchical data. I said it right. That's a really hard word for me to say. Hierarchical data here. So a very common sort of tree structure is your file system, right? We've worked with file systems before here. So let me go documents and GitHub, right? This is a tree, right? The root of my tree is C. That's the top level. Everything inside of C, then, right, is a child of C. All these other folders are children of C, and trees are recursive in nature. So every child in a tree is another tree, right? Eventually, you might end up with what we'll call a branch, or no, a leaf, right? It's just a file here. There's no other children there. It's just a leaf here. Anything that's a folder is another tree inside of itself that has other values here. I'm going to let that setup one of users. So the users folder, right? This is another tree. It has subtrees inside of it. This is a tree that has subtrees inside of it here. This is a tree that has subtrees inside of it. This is a tree that has subtrees inside of it. This is a tree that has subtrees inside of it. 2001. Where do we go here? This is a tree that has subtrees inside of it. Finally, we get to one that doesn't have subtrees anymore, right? It only has leaves. That's okay. Right? So it's this recursive nature here when we generate our trees, so we can store things in this hierarchical nature. Other common things, remember when we did our inheritance example, we talked about how we classify creatures. We have the kingdom, phylum, class, order, family, genus, species. That's a tree structure, right? The kingdom is the top level. Everything that's underneath it belongs to that. They're all in the same kingdom, right? And then lower down, it's another classification. Everything belongs to that is a child of it here. So you can do other sorts of interesting ways of storing data that we didn't have before. Right? We didn't really have a way to say, hey, here's the top level and everything belongs to me here. So a very basic tree here gets to be a little crazy, but you can. So we're going to go make a new class here. What week is this? This is week 10. Wow, week 10. This is trees here. And trees is where the book starts to get exceedingly wonky with its use of inheritance. It will go down this like 7 different class inheritance path here, and it drives me crazy. It's very efficient, very nice, very useful, but in terms of like reading one and trying to figure out what it's doing, I feel like it's a big pain. So I will try not to use all that crazy inheritance, and you can go look at the book and see how he does it here to appreciate how smart he is. I'm just doing it. Here's a quick, easy way for me to look at and understand it here. I'm not as smart as the author. I've never written a textbook. That's okay. Um, feel like maybe I should because people make a lot of money off of them, but then I would just feel bad making people pay outrageous fees for a textbook when we've got all the internet, all this info online. So that's okay. All right, so if we want to write a class for tree here, tree has what we'll call is a root. Yeah, sure. Use that one. Why not? Why did I not have a Python interpreter? So in our init here, when we make a tree here, maybe we want to give it some data here. Maybe we don't here. Well, we'll start with nothing here. So we'll say, hey, the data that I'm storing is none to start, right? So you haven't given me anything here. And then I've got a list of children here, some number of children, okay? So things you can do then, you can set my data here, and then we'll say, let's have a add child here, given something here. Maybe we should take some data here. We'll do that. We'll say, hey, you've got to give me some data. So the data is the data here. So if you give me another piece of data here to add as a child here, I'm going to say myself.children append tree given that piece of data. Right? It's recursive. It's another tree with a piece of data, another tree with that piece of data, another tree with that piece of data here. So if we don't have any children, we're a leaf. all we have is data. There's no other children here. So we can say, hey, is leaf here? We're going to return the length of self.children equals 0. If the length of our children is 0, we have no children, then we're a leaf. If we're not a leaf, we have other children that are, we can go through and get the children and go do something with those as well, right? Now, this gets to be a little obnoxious to use, but we can do something like that. So you can say, okay, here's my what's it? Kingdom. What's the name for that? Kingdom Final Class. It's the
Classification system.
classification system. There we go. Equals a tree, and the first level then is the kingdom. Okay, so my classification system dot add a child. So under kingdom, then right, we have phylum. Phylum. No, this one's actually not gonna. This is not gonna do what I want here. Sorry. Um, let's build out specific ones here. So what is the kingdom? Is that Mammalia? Mammalia. Male. Mammalia here. Mammalia. So I recently learned about this really cute animal here, the quokka. Quokka? Is that how you say it? This thing is adorable. Um, Rare species in this tiny little spot in Australia because Australia is nuts here. I'd love to go sometime, but I'm scared of spiders and snakes and other things here. So I don't know if I'll ever go here. Um, but quokkas are adorable here. So what is their classification here? So they're kingdom Animalia. Oh, Animalia, not Mammalia. That's the class here. So animal, and then my classification system. I want to add a child here, so that's the Animalia kingdom there, and then we'll add a Chordata phylum to it. Okay, whatever this one is here, and then now I need to go get that one out. Right, so this is the Chordata is my classification system dot children of 0. This is not the best way to go get it here, but it's okay. So we've got some number of children here. So now we've got Chordata, and I can take Chordata and I can add a child. Now we can add Mammalia, right? Well, here's all the mammals here. Okay. And then again, I need to go get that one back out. So Mammalia is my Chordata dot children of 0. I haven't added more than one yet here. We'll get there eventually here. So after we do mammals, we can do this one. Let's add infraclass. Did they add to this here? It's been like 20 years since I took biology. Probably overdue that they changed this thing here. We'll pretend it's not there. Here, we'll just go right to order. So Mammalia dot add a child here. Add this one here. And then let's go look up us here. Or should we do like chimps? Chimps are fun too. How about a lemur? I want to know what lemurs are in. Um, my kids have been watching Madagascar lately, but the 2-year-old is scared of the king for some reason. He thinks he's scary, which is the cutest thing because like it's not cute that he cries, but like when he shows up and starts dancing around, being all happy, he like cries and he's scared of him. Um, so he is in Mammalia, but this is the primate order here, right? So we'll take Mammalia and we're going to add another child to it then for primates. Okay, and then let's pretend like there's not the other ones here because I don't want to have to do a whole lot of typing here. So then whatever this thing is here, we'll say is my Mammalia children at 0, right? And primates then is my Mammalia children at index 1. Right? We're finally kind of branching out here. We've got different classes here. And then we'll take this one and we'll add a child of the quokka here. And then we'll take primates and we'll add a child of the lemur. Right? Again, we'd have other levels and other things here. We just don't want to add tons of them here. We're adding this sort of hierarchical data. Right? It's this tree structure where my root here is the classification system. That's the very top. It doesn't have any parents. This is it. And then I can track down my children, track my children, track my children, track my children here. Um, so we're storing them in this sort of list here. So as long as I know what the root is, I can go get to it, right? So if I wanted to print these out then, right, if I wanted to write a function for printing my tree here, let's write a function for print here. This gets a little bit messy here, but it can be recursive, right? Because all of my children are also trees, I can go and print them as well. I can call it recursively here. So we're going to print out the self.data, right? And then for child in self.children, we're going to call child.print. We This is probably not. I don't want to reuse name print here. How about print tree? There we go. Make that a little bit more distinct here, right? So we'll just output whatever our result is, and then for every child, we'll have it do the same print tree function here, and we'll print itself and print all of its children. Print itself, print all of its children, right? So eventually we can run this one here then, and we can go print our tree. So we're going to call what was that classification system dot print tree here. We should get back out all the info we put in here in Animalia, Chordata, Mammalia. Now, you'll notice the order that this is happening here is going deeper and deeper and deeper here into the Mammalia, whatever, to find the quokka before it gets to primates, right? Because when we printed here, we said, okay, print yourself and then print all of your children recursively. So the first child will go in and print itself and then print its first child, which will go in and print itself and print its first child. So you're going deeper into the tree, not broader, right? Not one level at a time. Right? So this is print tree. We call this depth first. So it'll go deep first and then come back out. So you can also print it breadth first here, where you print each level at a time. Breadth, that's probably a word there. So to do that one, we're going to print ourselves. And then instead of recursively calling our child first, we want to print all of the children. And then we want each of them to go and recurse here. So it gets to be a little bit weird how it does this one here. So we want to print the child, but not have it keep on recursing right away. So what we can do then is we can make a queue of items here. Gets to be a little bit funny here. But we want a queue. Here's our items queue, right? Really can just be a list. We'll just add to the front, or I'm sorry, add to the back, take from the front here. It's probably okay. So we're going to keep adding, or maybe we'll just call this items is fine here. So we'll take our items and we're going to append the self.data, and then for child in self.children, right, we're going to, we can pass in this, right? So we need to pass in, we have a little helper function here. So here's the print tree, breadth first here, that takes the self data and the queue. So for each child here, then we're going to recursively call and hand it the queue that we keep working on, so we can keep adding items to it here. So we'll add the items to it. So say child.print tree breadth first given the items list here. So each one of these here can go and add itself to the list here. Then we can go print them all out, and then we can recurse into them here. Because we want to print each item, and then we want to recursively call where it goes at the next level and prints all, and goes to the next level and prints all, and goes to the next level and prints all of them here. So we don't need to put them in the right order here is essentially the piece of it. So we're going to add them all in. Is it? That's probably not the right term for it here. So to print, we'll get our list of items. We'll append ourselves, and then we need to go to the next generation and print all of them out, and go to the next generation and print them all out here. So that's just for every first level. You have to go add them in. Oh goodness, I might have to go copy paste from the book here. I don't. There's a particular syntax. I'm not remembering which one it is here. Why don't we call it good for today? I'll look it up. We can do it on Thursday, and you won't have to watch me scramble back and forth to figure out which way it is here. Um, but we want to do one level at a time here. Um, that's another way to traverse this tree. And then after this, we'll stop doing these trees that just have n number of items here, and we'll focus specifically on trees that are binary trees, trees that just have two children, a left child and a right child. And then we can build out a priority queue using that, which is a lot of fun here. Priority queues are really neat. So this was the like n tree here, and we'll move into that. Okay. We cover the project. We talk about the new project. Started with trees. We'll finish up trees on Thursday. Um, and moving along. Doing pretty good. Right. If you got any questions, let me know. If not, I will see you Thursday.